Welcome back. I am the Body Whisperer, and I am glad you are here. Before we begin, let us settle in together. Find a comfortable position. Let your arms grow heavy, your legs, your shoulders. Take a slow breath in and let it go. One more, in and release. Good. Now, while you rest here, doing nothing at all, something quiet is happening inside you. Your body is working. It always is. Every hour of every day, without ever asking for thanks. I want you to get to know it a little better, to listen to it, to feel it, to appreciate it. Because the more you understand the quiet world beneath your skin, the more at home you feel inside your own body. So come and meet Oxidative Ollie, one small part of you that keeps working through the night while you sleep. This is the story of 2 hours of antioxidants and free radicals to fall asleep to. There is nothing you need to do now, nowhere to be, nothing to figure out. Just breathe. Close your eyes if you have not already, and let us begin. There is a quiet piece of work going on inside you right now, and it has been going on every night of your life. The lights are off, the day is done, and somewhere in the soft, warm dark of the brain, the body's most expensive real estate, the organ that burns more fuel per ounce than almost anything else you carry, a figure in a worn canvas apron picks up his broom. His name is Oxidative Ollie. He is the night janitor. He has been here before, of course. Every night, same corridors, same quiet hum of sleeping tissue, same amber glow from the membranes that line the brain's long neural pathways. He knows the layout better than anyone. He knows where the debris collects. He knows which corners hold the most and why. And the thing Ollie knows, the thing that shapes every pass of that broom, is this. The brain is never truly clean when the day ends. The price of thinking, of every word recalled, every decision made, every moment of focus held together, is a kind of exhaust. Small, invisible, ordinary, not dramatic, just real. Here is the thing about energy. The brain consumes it at an astonishing rate, far out of proportion to its size. To do that, it burns oxygen constantly through a process that is elegant and efficient and also slightly messy. The mess is not an accident. It is chemistry. When a cell converts fuel into usable energy, the reaction leaves behind small, unstable fragments of oxygen, molecules that have lost an electron or gained one and are now restless for a partner. These fragments are called reactive oxygen species. That name sounds technical, but the idea is simple. They are the sparks left over from burning fuel, the ordinary exhaust of a living cell. In small numbers, those sparks are handled easily. The body knows about them. It has been managing them for as long as cells have been burning oxygen, which is a very long time indeed. But the brain is a special case. Its membranes, the thin, flexible walls that wrap every nerve fiber, every signal relay, every connection between thought and action, are made largely of fat. Rich, complex, beautiful fat. And fat is exactly what a reactive oxygen fragment most likes to grab at. That is why Ollie's work is here, in the brain, and not somewhere else. The fragments drift through the neural tissue the way dust drifts through a sunlit room. You cannot see it happening. The room looks fine, but the dust is there, and without someone moving quietly through it with a broom, it accumulates on the membranes, near the proteins that carry signals from one neuron to the next, close to the long, careful strands of genetic material that every cell keeps folded neatly at its center. Not a flood, just enough. Ollie is not here because something has gone wrong. That is worth saying plainly, and he would say it himself if he were the kind to stop and explain himself, which he is not. He is here because this is how the body works. The debris is ordinary. The cleaning is ordinary. The night is when the cleaning catches up. The brain has its own cleanup crew, a set of molecules it builds from simple raw materials designed to meet those reactive fragments and quiet them before they do harm. The most important of these is a molecule the body assembles itself, called glutathione. Think of it as the janitor's main tool, a small, three-part compound that can approach an unstable oxygen fragment, offer it the electron it is looking for, and render it harmless. The membrane is safe. Ollie moves on. There are also two enzymes, proteins that function like specialized machinery that handle the most reactive fragments before glutathione even needs to arrive. One of them breaks a particularly sharp form of oxygen exhaust into something far gentler, a process that happens so quickly it is finished before any damage begins. The other takes the gentle result of that first reaction and converts it all the way down to ordinary water. Plain water. Nothing left to cause trouble. The body is not improvising any of this. It has been doing it, in one form or another, for an enormous stretch of evolutionary time. These are not emergency measures. They are maintenance. Regular, dependable, nightly maintenance. And the balance between the debris and the cleanup, that is the real story of what Ollie does. When the balance holds, the brain's membranes stay supple. The proteins at the synapses, the tiny gaps between nerve cells where one neuron passes a signal to the next, keep their shape and keep their function. The genetic instructions inside each cell stay legible. When the balance tips, when the debris outpaces the crew, even a little, for long enough, the body gives that imbalance a name. Researchers call it oxidative stress. A slow drift, the kind of thing that accumulates over many days, many nights, many years of burning fuel and not quite keeping up with the sweeping. Ollie knows this. He has always known this. It is why he shows up every night without being asked. It is why he works the neural corridors while the brain is quiet, and the signals have slowed, and the membranes are finally still enough to be tended. The day burns, the night restores. That is the arrangement. It has always been the arrangement. So let the breath settle. Let the weight of the body sink a little deeper into the surface beneath it. The work is already underway. Ollie is already moving through the first corridor, broom in hand, in no particular hurry, doing what he has always done. Everything in the room is exactly as it needs to be. The dark is doing what dark does best. You can let it. The first corridor is narrow, not dark exactly, more like dim, the way a room looks when the last lamp has been turned off, but the street light still finds the window. The brain is never entirely still. Even in sleep, signals travel, temperatures drift, tiny adjustments are made. Ollie moves through all of this without disturbing it. He has done this long enough to know how. Here is what he is actually looking for. A cell in the brain, any cell, a neuron, a supporting cell, any of them, is wrapped in a membrane. Think of that membrane as a flexible, double-layered sheet made almost entirely of fat. Not the stored kind, the structural kind. These fats, called lipids, are what give a cell its boundary, its shape, its ability to hold what is inside and keep the outside out. They are also what makes the brain so unusually rich in fats, compared with almost any other organ in the body. The brain is, in a very real sense, mostly fat and water. A humble description for the most complicated structure in the known universe. Now here is the thing about fat and oxygen together. When a cell burns fuel, and the brain burns a remarkable amount of it, far more than its size would suggest, the process leaves behind small, unstable molecules. Fragments, really. These are the reactive oxygen species Ollie is here to collect. And what makes them worth collecting is this: they have a missing piece. A molecule that is missing a piece will reach for the nearest available one. In the brain, the nearest available piece is almost always a fat molecule in a membrane. When a reactive fragment grabs onto a fat in a membrane, it sets off a small chain. That fat becomes unstable itself. The newly unstable fat grabs at its neighbor. The neighbor grabs at the next one. Researchers call this process lipid peroxidation, which simply means the slow chemical unraveling of membrane fat. One fragment can trigger several more before the chain runs out of reach. Ollie knows this. This is why the brain's great richness in fat, the very thing that makes it what it is, also makes it the place where this kind of wear accumulates most readily. A tissue that runs on fat is a tissue with a lot to lose. Not all at once. Never all at once. Just slowly, one membrane at a time, one chain reaction at a time, across the long arc of a life. Ollie's broom is not a real broom, of course. What he carries is something more like the body's own antioxidant system made visible. The main tool is glutathione, a small molecule that the body assembles from 3 simpler building blocks, and which the body keeps in remarkable supply inside every brain cell. Glutathione works by offering itself. When a reactive fragment is looking for something to grab, glutathione steps in. The fragment takes what it needs from glutathione instead of from a membrane fat. The membrane is left alone, and then something remarkable happens. Glutathione, having done its job, is not simply used up and discarded. It is rebuilt. Another molecule, a quiet, tireless carrier that cycles through hundreds of reactions in the same cell, hands over what glutathione needs to be restored. The used form becomes the fresh form again. It cycles. The same tool, refreshed, ready for the next fragment. This is what makes the antioxidant system feel less like a supply of something and more like a living, breathing process. It is not a tank that empties. It is closer to a wheel that turns, provided the energy to turn it keeps coming, and provided sleep gives the system the time and the quiet to keep cycling without the added demand of a waking, working brain overhead. But glutathione is not the only tool in this corridor. Before a reactive fragment even reaches a membrane, 2 enzymes take a first pass at the most reactive kinds. The first, called superoxide dismutase, meets the sharpest fragments right at the point where they are formed, inside the cell's power stations, where fuel is being turned into energy and the exhaust is freshest. It converts those fragments into something less reactive. The second enzyme, catalase, meets what comes next, a molecule called hydrogen peroxide, which is itself a byproduct of that first conversion. Catalase breaks it down the rest of the way into water. Plain, unremarkable water. The most reactive thing in the corridor becomes, in 2 steps, something you can drink. Ollie has always found this sequence quietly impressive, not because it is unusual. It happens in every cell, every moment of the day and night, but because of what it represents. A living system that anticipated its own exhaust and built the cleanup into the machinery. The debris was never an afterthought. The solution was never an afterthought either. He rounds the corner at the end of the first corridor and moves into the second. The membranes here are quieter. Less traffic during the day means fewer fragments left behind, and fewer fragments means the enzymes in glutathione have had an easier time of it. Ollie notes this the way a janitor notes a clean section of floor, without drama, without lingering. Some corridors need more attention than others. It did not make the work smaller. It made it knowable. Let the breath out slowly. And again, there is no right way to do this. There is only softer and then softer still. It did not make the work smaller. It made it knowable. And knowable is enough when the hour is this quiet. Ollie moves further in now. Not toward any particular address. The brain does not have those. It has neighborhoods. Dense ones, where the axons run close together and the membranes stack up layer on layer, insulating signals the way rubber wraps a wire. These are the places where the fatty surface area is greatest, and so the places where reactive fragments have the most to reach for. Ollie has always paid closer attention here, not because the chemistry changes, because there is simply more of it. Here's the thing most people never quite consider. The brain is the hungriest organ in the body, by some distance. It does not lift anything. It does not push blood or filter waste or move a limb. And yet it burns fuel at a rate that would seem almost unreasonable if the results were not so obviously worth it. All of that burning, turning oxygen into usable energy, moment after moment, through every waking thought and every sleeping consolidation, leaves behind the ordinary exhaust of that process. Small, reactive molecules, fragments. The kind of debris that has to go somewhere. Most of that somewhere is Ollie's department. The exhaust does not come from nowhere. It comes from the cell's power stations, those small bean-shaped structures inside nearly every cell in the body, converting fuel to energy through a process called oxidative phosphorylation, meaning the cell strips electrons from fuel molecules and uses the movement of those electrons to build usable energy. It is efficient. It is not perfect. Some electrons slip loose before they finish the circuit, and when a loose electron lands on an oxygen molecule, you get one of those reactive fragments, a superoxide, meaning an oxygen molecule carrying one extra, unwanted electron. That is all a free radical ever is. Not a villain, just an electron that ended up somewhere inconvenient. Mia would be the first to tell you that this is simply the cost of output. She manages the power stations, each one running its own small version of this process, each one producing its own small share of slip. Every station leaves something behind. That is thermodynamics. Mia has never lost a moment of sleep over it, though she would appreciate you noting the irony. She runs her audits through the night, quietly retiring the stations that are wearing out, the ones whose electrons slip more than they should. And she does this without drama, without announcement, without any particular acknowledgement that the rest of the system might be grateful. Ollie is grateful, in the way that someone is grateful for a colleague they do not see very often, but whose work makes their own possible. Fewer worn-out stations means fewer stray electrons. Fewer stray electrons means fewer reactive fragments. And fewer reactive fragments means the cleanup crew can keep pace. That keeping pace is the whole thing. There is a term researchers use for when the cleanup falls behind: oxidative stress. It does not mean anything dramatic. It means the balance has tilted. More reactive debris than the system can comfortably quiet. The antioxidant crew is still there. They are not gone. They are just outpaced, the way a single person with a mop cannot quite keep up with a very large leak. Ollie knows this. The brain, wrapped in all that delicate, fat-rich membrane, is the place where a tilt like that matters most, not because the consequences are sudden, but because the fats that make up those membranes are particularly easy to reach for, And because a membrane that has been grabbed at too often begins, slowly and quietly, to change. Not even this week, but over years, the difference between a brain whose cleanup keeps pace and one whose cleanup lags becomes the difference the body simply calls aging. Ollie is not trying to stop aging. Nobody here is trying to stop aging. This is maintenance, the way oiling a hinge is maintenance. Not because you believe the door will never wear out, but because a well-oiled door works smoothly for much longer than one that was left to rust. And maintenance, it turns out, is mostly about timing. The brain cannot run its deepest repair work while it is also running everything else. The signals flying between cells, the attention tracking a screen, the low hum of sorting through whatever the afternoon left behind. All of it uses the same resources. The enzymes that break down reactive fragments, the molecules that cycle back from their used-up state into ready-again state. They are slower when the brain is busy, not absent, just slower. The balance tilts a little further each hour of the day, like water slowly finding its level. Sleep is when the level is restored, not because sleep is magic, because sleep removes the competition. The signal is quiet, the attention lifts, and the cleanup crew, no longer sharing the available resources with every other demand of the waking brain, gets something closer to a clear run. Ollie has the corridors more or less to himself now. That is not an accident. That is the design. It did not make the work easier. It made it possible. You are drifting now, slowly and gently, the way a small boat drifts from the shore. No hurry, no direction to hold. There is a question worth sitting with for a moment, not a complicated one. Just the kind of question that once you have it, you cannot unfind it. Where does the cleanup go? Ollie moves through the brain's fatty corridors, the long, pale axons wrapped in their insulating sheaths, the membrane-rich synaptic endings where signals leap from one cell to another, and he clears reactive debris. Small, unstable oxygen fragments, grabbed before they can grab something important. He quiets them, and then they are gone. But the tool he uses to quiet them does not simply vanish along with them. That tool changes, and the change is the whole story. The cleanup molecule, the body's primary antioxidant, the one the cells assemble from 3 small building block amino acids called glutathione, does not get used up in the way a paper towel gets used up. It gets changed. There is a precise word for what happens: oxidized, meaning it gives away something of itself to quiet the fragment it encounters. In doing so, it becomes a slightly different thing. A spent form, still present, still structurally intact, but no longer able to do its job. In the language of the cell, this spent form is called oxidized glutathione. The active form, the one ready to work, is called reduced glutathione. Those two words, oxidized and reduced, just mean the molecule has given something away or gotten it back. Like a sponge soaked full versus a sponge wrung dry. One is ready to absorb. One is waiting to be refilled. Ollie knows this. The remarkable thing, the thing worth pausing for, is that the cell does not discard the spent form. There is a small, diligent enzyme whose only job is to take the spent glutathione and restore it to working order. That enzyme is called glutathione reductase, meaning it is the worker that reduces the spent form back to the active one. It runs this conversion continuously, as long as the raw material it needs is available. And what it needs to do that work is a molecule the cell keeps in careful supply, a carrier that shuttles a tiny packet of chemical energy to wherever it is needed. That carrier has a long name, but it functions like an internal rechargeable battery, something that accepts a charge in one place and delivers it somewhere else. The cell uses it everywhere, simultaneously, for hundreds of different tasks. Glutathione reductase is simply one more stop on its endless route. So the cycle runs like this. A reactive fragment appears. Glutathione meets it. Glutathione gives something of itself to quiet the fragment and becomes the spent form. Glutathione reductase collects the spent form, recharges it using that cellular battery, and returns it to service. The fragment is gone. The tool is back. Not a one-way process, a loop. This is what makes the antioxidant system so different from an ordinary supply of something that gets used up. A warehouse of materials runs down. A cycle, if it is fed, runs on. The brain does not stockpile finished antioxidant and hope it lasts the night. It runs a quiet factory that makes more as fast as it spends. Ollie moves along a long, myelin-sheath fiber, one of the brain's white matter highways, densely packed with fats, running signals from one region to another. And he understands that the work he does is not really about how much glutathione is present at any given moment. It is about how quickly the cycle can turn, speed of recycling, tempo of restoration. That is the real measure of whether the cleanup is keeping pace. And the tempo, it turns out, is slower when the cell is under strain. When the day has been long and the fuel burning intense, the reactive fragments arrive faster than usual. The spent form of glutathione accumulates. The reductase enzyme works as hard as it can, but the battery it depends on is also in demand elsewhere. In every other energy-hungry reaction, the cell is running simultaneously. The cycle does not stop, but it slows. This is not a failure. It is just arithmetic. The demand side of a ledger running briefly ahead of the supply side. And sleep is when the ledger levels out. During waking hours, the cell's shared resources are pulled in dozens of directions at once, maintaining electrical signals, repairing proteins, managing the constant traffic of messages crossing its membrane. The antioxidant cycle competes for its share of that energy budget alongside everything else. In sleep, the electrical traffic quiets. The membrane is no longer fielding signal after signal. The shared cellular battery is less contested, and so the reductase enzyme gets a larger, steadier share of what it needs to keep turning. The cycle picks up. The spent glutathione clears faster. The active form builds back toward its full working concentration. Not a surge, Nothing in the brain's chemistry surges at this hour. Just a steady, unhurried recovery of pace, the way a path gets easier to walk when the crowd thins. Ollie knows this hour. He does not rush. He has never rushed. The corridor ahead is long and quiet, and the cycle behind him is already refilling everything he has spent. The work is not heroic. It is structural, built into the rhythm of the cell so completely that it does not need a decision or a signal to start. It did not make the night faster. It made itself sustaining. Let the back settle into the mattress. Let it take your weight completely. It has been waiting all day to do that. It did not make the night faster. It made itself sustaining, and yet Ollie is not working alone. That is the thing worth sitting with for a moment. The picture of one quiet figure, sweeping reactive fragments from fatty membranes, is a true picture. But it is not the whole picture. The brain's antioxidant system is less like a single janitor and more like a crew, each member passing the problem to the next, each one handling what the others cannot. Ollie moves through this network the way a night shift worker moves through a building that has been designed carefully to make the work possible. Here is how that design works. Glutathione is the workhorse, the central tool, the molecule that steps in and absorbs the charge a reactive fragment carries, quieting it before it can grab at a fatty membrane or tangle in a working protein. But glutathione does not operate at the first stage. There are fragments that are simply too reactive, too fast, too electrically hungry for glutathione to meet head-on. Something has to step in earlier. That something is the enzyme that breaks apart the most reactive fragment of all, a molecule called a superoxide, which the mitochondria shed almost continuously as a byproduct of burning fuel. This enzyme, superoxide dismutase, meets the superoxide before it can do anything and converts it into something far less reactive, a simpler compound called hydrogen peroxide. Still not harmless, but slower, less grabby, more manageable. Hydrogen peroxide is, in its way, a holding category. The cell has taken a very reactive problem and turned it into a moderately reactive one. That is progress. But the work is not finished. A second enzyme, catalase, picks up where the first left off. It finds the hydrogen peroxide and splits it cleanly into two things that are entirely harmless: water and ordinary oxygen, both of which the brain is glad to have. Neither of which will tear at a membrane or tangle in a strand of DNA. So, the sequence runs like this. A stray electron becomes a superoxide. The first enzyme converts it to hydrogen peroxide. The second enzyme converts that to water. 3 steps, 3 different tools, 1 outcome. The reactive thing is made harmless, quietly, before most of the cell's machinery ever notices it was there. Glutathione handles what remains. The fragments that slip past, the ones produced by a different route, the slow background oxidation that is simply the cost of being a warm-blooded animal burning fuel at the rate the brain does. Glutathione meets them, absorbs them, becomes spent, and then, as the previous stretch of this work described, the recycling enzyme restores it, and the loop begins again. Ollie knows this dark, knows the sequence by feel as much as by reason. The network is not a chain where one break stops everything. It is layered, redundant, built by a few billion years of trial and correction into something that handles the ordinary load with room to spare. What changes that margin is demand. During a full day of thinking and reacting and remembering and deciding, the brain burns fuel at a rate that few other organs approach. The mitochondria, those amber-orange power stations whose inner folds run the chemistry of energy production, are running hard. And as they run, they shed reactive fragments at a proportionally higher rate. Not because anything has gone wrong, because that is the physics of the reaction. You burn fuel, you get exhaust. The exhaust here is measured in molecules rather than smoke, but the principle is the same. Mia, the facility manager of those power stations, understands this without sentiment. Every station leaves something behind, she would note, if pressed, and she would consider the matter closed. The leaving behind is not a flaw in her operations. It is the ordinary cost of the output her stations provide. What happens to what is left behind is, in her view, a separate department's concern. Ollie's department, as it happens. And through the sleeping hours, that department has an advantage it cannot have while the brain is awake. The demand for the shared cellular resources, the energy carriers, the cycling molecules, the enzymatic machinery, drops. Not to zero. The sleeping brain is not an idle brain, but the competition drops. The antioxidant system does not have to argue for access to the resources it needs. They become available in the way a quiet building becomes available after hours. The same resources, the same rooms, but without the crowd. The two-enzyme sequence, superoxide dismutase, then catalase, runs at its own tempo through this. It does not speed up dramatically. It does not need to. It simply runs without interruption, without competing requests pulling the shared machinery in another direction. The fragments are met at each stage. The chain is broken before it can extend. The membrane is left intact. That is the real gift of these hours. Not speed, not a surge of repair, just uninterrupted tempo, sustained through all the corridors of the brain that the waking day had no time to reach. Ollie moves through those corridors now, past the long axons wrapped in their fatty sheaths, past the branching dendrites with their delicate tips, past the junctions where one nerve cell speaks to another, where the membrane's integrity is everything. Every pass is a quiet one. Every fragment met is one less fragment lingering. It did not make the work dramatic. It made it complete. The day has loosened its grip. Whatever it was carrying, it can put down now. You are allowed to be finished with it. There is a part of the brain that most people have never thought about, though it makes up roughly half of what sits inside the skull. Not the gray outer layer where thinking happens, but the white matter, the long cables that carry signals between one region and another. Those cables are wrapped in a fatty insulating coat called myelin. And myelin, being fat, is exactly the kind of surface a reactive oxygen fragment finds easy to grab. Ollie knows this. He has walked these corridors 1,000 nights. Myelin is built the way electrical wires are built, a conductor wrapped in insulation. Strip the insulation, and the signal falters. The body does not want that, so it protects the myelin the way it protects every fat-rich membrane in the brain, with a standing guard of antioxidant activity, maintained through the waking hours as best it can, and deepened and restocked through the sleeping ones. Here is what makes myelin different from an ordinary cell membrane, though. It is wrapped in layers, tight, concentric rings of fat stacked around a nerve fiber the way a bandage is wound around a finger. More layers means more surface. More surface means more places where a stray fragment from the day's fuel burning can begin a chain reaction. The kind that does not stop at one molecule, but pulls the next one and the next along with it. Lipid peroxidation is the name for that process. And in the white matter's layered corridors, it has more room to run than almost anywhere else in the brain. Hurrying is not the answer here. The answer is coverage, making sure the antioxidant presence in these corridors does not thin out in any one place long enough for a chain to build. He moves steadily. He always has. What is interesting is that the brain has a kind of internal geography when it comes to this work. Some regions are more demanding than others. The areas that fired most heavily through the day, the ones that handled noise and decision and motion and light, carry a denser residue of reactive fragments into the sleeping hours. The white matter corridors that connect those high-demand regions bear a heavier load. Ollie learns the map over time. Every brain has its own version of it, and the map shifts. A day of steady, unhurried work leaves a different residue, and a day of sustained strain, not dramatically different. But the antioxidant crew reads the difference and adjusts, not by changing its fundamental tools, but by routing its attention to where the demand is highest. Glutathione concentrates where it is needed. The enzymes that handle the first stages of the work, converting the most reactive fragments into something less reactive, and then into water, run at a pace that the regional load sets. There is an elegance in this that is easy to miss. The brain does not post a sentry at every possible location and wait for trouble. It maintains a baseline, and it responds to signals. The signals are the fragments themselves. When the concentration of reactive debris rises above a certain threshold in a given area, the local antioxidant response rises with it. Not perfectly, not instantly, but reliably, the way a river finds its level. This responsiveness has a name. Researchers call it redox signaling, the idea that reactive molecules in small quantities are not just exhaust, but information. A fragment appearing at a junction between nerve fibers is not only something to be cleared. It is a signal that clearing is needed there. The cleanup crew reads the message and responds. The fragment, having delivered its message, is then quieted. Ollie would not describe himself as a reader of signals. He would say he follows the work. But the work and the signal are the same thing. This is what makes the balance so delicate and so ordinary at the same time. Too few fragments and the signaling goes quiet. The system loses information about its own state. Too many and the signal drowns in noise. The cleanup crew falls behind, and the slow accumulation begins that researchers call oxidative stress. The range between those two states is where healthy cells live. Not sterile, not flooded. Balanced. Sleep is when the balance is easiest to hold. Through the waking hours, the brain burns fuel at a rate that keeps the fragment count near the upper edge of that range. The antioxidant crew works hard to keep pace. But the margin is narrow, and by late afternoon, after a full day of burning and signaling and thinking, the margin has narrowed further. The crew has not failed. It has simply been occupied. And then the lights go out, and the fuel demand drops, and the fragment count begins to ease back from that upper edge. The crew, with fewer new fragments arriving, can turn its attention to the corridors it had to leave for later. The myelin sheaths, the junctions between regions, the long, fatty cables of the white matter that spent the day carrying 10,000 signals in every direction and now lie quiet in the dark. Ollie moves through them without a sound. The work here is the same as everywhere else. Quiet the fragment, restore the membrane, keep the chain from building. But in these corridors, in this silence, the work feels like something more than maintenance. It feels like what the night was designed for. Not a rescue, just a return to order. Let the thoughts go where they want to go. You do not have to follow them. One drifts past, and then another, and then nothing at all. Not a rescue, just a return to order, and order, it turns out, requires fuel of its own. Ollie has spent the earlier part of the shift moving through the brain's fatty corridors. The long white pathways, the dense gray folds, the wrapped sheaths of myelin that insulate the brain's signal lines. The reactive fragments have been met. The enzymatic sequence has been running. Superoxide handed off to hydrogen peroxide. Hydrogen peroxide handed off to water. Glutathione cycling through its loop. Spent and restored, spent and restored. But here is the thing nobody usually stops to ask. What powers the cycle itself? The enzymes do not run on nothing. The glutathione loop does not renew itself by wishing. Every step in the antioxidant sequence, every handoff, every conversion, every moment of restoration, draws on a carrier molecule that moves through the cell like a shared currency. That currency is a small but essential compound the body assembles from a vitamin-like building block. Researchers call it NAD, short for nicotinamide adenine dinucleotide, though the name matters less than the job. Think of it this way. The antioxidant cleanup crew needs more than instructions. It needs purchasing power. NAD is that purchasing power. Without it, The enzyme that restores spent glutathione, glutathione reductase, cannot complete its work. The recycling loop slows, spent glutathione accumulates, and the chain of reactive fragments that glutathione was meant to interrupt grows a little longer before it is stopped. This is where a quieter figure enters the scene. NAD+. Nancy moves through the cell not as a single actor but as a kind of atmospheric condition. She is the universal energy carrier of the cell, a flat double ring molecule in warm gold, cycling constantly between a charged state and a spent one, carrying electrons from one reaction to the next and releasing them where they are needed. She does not take credit for individual outcomes. She is present in hundreds of reactions simultaneously, and she has always been that way. Her catchphrase, if she had one, would be quiet and understated. She powers the ones who power everything else. What makes her relevant to Ollie's work is specific. When the cell's energy demands are high, when neurons are firing, when signals are racing down myelin-wrapped axons, when the waking brain is burning fuel at its daytime pace, NAD is drawn toward those demands. The mitochondria claim a significant share of it. The signaling pathways claim more. The antioxidant loop gets what is left. This is not neglect. It is ordinary cellular economics. There is only so much currency in circulation at any given moment, and it flows toward the loudest demand first. But as sleep deepens, as the brain's firing slows, as the long-distance signaling quiets, as even the mitochondria ease their tempo during the lighter stages of early rest, the demand for NAD drifts down. Not to zero, never to zero in a living brain, but enough. Enough that the antioxidant loop can draw its full share. Ollie knows this. The restoration of the glutathione cycle through the sleeping hours is not only a matter of fewer reactive fragments arriving, it is also a matter of more NAD available to power the recycling. Both things happen together. The supply of debris falls, and the capacity to process it rises. The balance tips back, one quiet corridor at a time. And then there is the repair work that follows the cleanup. When a reactive fragment has already reached a strand of DNA, not a dramatic event, just the ordinary small contact that happens across billions of cells every day, the cell has its own repair enzymes waiting. Those enzymes also draw on NAD. They are called PARP enzymes, which stands for a long name that means simply proteins that locate damage along a DNA strand and signal for its correction. PARP enzymes are not dramatic. They do not announce themselves. They move along the double helix the way a careful inspector walks a length of rope, looking for fraying, noting it, flagging it for the crew that follows. And the crew that follows needs NAD too. This is why the sleeping hours carry a kind of layered generosity. The same easing of demand that allows Ollie's enzymatic sequence to run at full tempo also allows the PARP-guided DNA repair to proceed with fewer interruptions. The shared currency flows more freely. The work that was deferred through the afternoon and evening, the small corrections, the quiet restorations, gets done. None of this requires drama. The cell does not know it has been waiting. It only knows that the resources are available now, and so it works. There is a certain elegance in that. The body does not schedule repair the way a hospital schedules surgery. It simply leaves the work undone until conditions allow. And then when the competition eases, the work begins on its own. The brain is not being fixed while you sleep. Nothing was broken. It is being maintained the way a well-kept building is maintained. Not because the roof is leaking, but because that is the nature of upkeep. Regular, unremarkable, necessary. Ollie moves through another corridor. The NAD is cycling. The glutathione loop is turning. The PARP enzymes are doing their quiet inspection down in the nucleus of cells too small to see without the sharpest instrument. Not a system under strain, a system at ease. Listen to how quiet it is between the words. That quiet is doing more for you than anything being said. A system at ease moves differently than a system at work. The corridors are the same, the tools are the same, but the tempo, that changes. And it is in the change of tempo that the brain's outer layer, the cortex, does some of its quietest and most necessary housekeeping. Ollie knows this layer well. The cortex is where the day is processed. Every conversation, every problem turned over, every moment of attention burning fuel and leaving its small exhaust behind. Through the waking hours, the reactive fragments accumulate in layers, not deeply, not catastrophically, but steadily. The way dust settles on a surface, you can only notice once the light is gone. When sleep arrives, the light changes, and the dust becomes visible. Here is something worth holding for a moment. The brain does not simply slow during sleep. Certain regions slow dramatically, yes, the parts that manage language, deliberate thought, the constant monitoring of the outside world, but underneath that quieting, a different kind of activity continues. The antioxidant machinery runs on. The recycling loops keep turning. The enzymes keep meeting the fragments they were built to meet. The brain is not resting. It is switching tasks. And the task it switches to, the one that gets so little attention because it happens without any drama, is the restoration of what researchers call redox balance. A balance between the reactive fragments produced by burning fuel and the molecules that quiet them. The word redox simply means the exchange of electrons. The same exchange that, when it goes slightly too far in one direction, leaves a fragment grasping at a nearby membrane. Ollie thinks of it as a ledger, not a dramatic one. Just a quiet column of debits and credits that the waking hours slowly tip one way and that the sleeping hours tip just as slowly back. The tipping back happens through something small enough to miss entirely. In the brain's fatty membranes, those long pale wrappings around each signal-carrying fiber, there is a molecule called vitamin E, or tocopherol. It sits inside the membrane itself, positioned at the water-fat boundary where reactive fragments are most likely to arrive. When a fragment reaches for the nearby fat and begins the chain of grabbing that Ollie works to interrupt, tocopherol reaches in first. It offers up one of its own electrons. The fragment accepts. The chain stops. Tocopherol is spent after this. It has given what it had. But here is the part that tends to get left out. Tocopherol does not stay spent. A molecule called ascorbate, what most people know as vitamin C, circulates just outside the membrane in the watery fluid beyond. It finds the spent tocopherol and hands it a fresh electron. Tocopherol is restored. Ascorbate in turn is spent, and then ascorbate is restored using the same cellular energy carrier, the same shared currency that restores glutathione. The whole outer layer of the antioxidant network is a chain of lending and return, each molecule handing off to the next, each one restored in turn by the one behind it. Not a single descender, a relay. Ollie does not run alone, he never has. The relay matters most in the membrane itself, exactly where the brain is most exposed. The fat-rich tissue that the brain is built from is precisely the tissue that reactive fragments find easiest to grab. Tocopherol, nestled inside that fat, is the first responder positioned where the threat first appears. The chain that runs from tocopherol outward through ascorbate and back through the glutathione recycling loop is the brain's way of keeping that first responder always stocked, always ready. During the waking hours, the relay runs under pressure. Fuel is burning, fragments are arriving. Every step of the relay is in use, and the shared currency that powers the restoration is being drawn on from many directions at once. As sleep deepens, the draw narrows. The fragments slow their arrival, and the relay, for the first time since morning, has the bandwidth to run at something close to its full design. The spent tocopherol gets restored faster than it was spent. The ascorbate cycle turns without waiting. The glutathione loop runs uninterrupted through the quiet corridors. Ollie knows this hour. He moves through the cortex's outer layers with a particular attention to the places where the membrane is thinnest, where the signal-carrying fibers run closest to the surface, where the waking day's activity left the most to restore. He is not hurrying. Hurrying is not the point. The point is coverage, steady, unhurried, complete. The relay hands off. The electron finds its way. The membrane holds. Somewhere in the soft dark, a breath deepens. The body settles further into the surface beneath it. The weight of the limbs spreads and quiets, the way water finds its level when the container finally stops moving. The brain is not asleep in the way the body is asleep. Quietly, deliberately, without any announcement, it is running the relay that the day could not quite finish. The first responder in the membrane gets restocked. The chain of lending and return completes its cycle. The ledger moves, one small credit at a time, back toward the middle. Not a sudden correction, a slow return. Nothing is required of you now. Not thinking, not planning, not remembering. A slow return. That is the shape of what Ollie does when you step back and look at the whole arc of a night. Not a dramatic reversal, not a system rebooted from scratch. just a long, unhurried settling, like a glass of water left on a windowsill after being shaken. The surface finds its level again. The brain finds its balance. And yet, the balance is more delicate than it first appears, because there is a wrinkle in the brain's chemistry that most people never hear about. A complication that sits quietly inside the same fatty corridors Ollie patrols, and that makes those corridors under the wrong conditions their own worst amplifier. Here's the thing about iron. The brain needs it. Iron is woven into the enzymes that build neurotransmitters, the molecules nerve cells use to pass signals to one another. It is part of the machinery that moves oxygen where it needs to go. Without iron, none of the brain's electrical work gets done, so the brain holds iron close. It stockpiles a careful reserve, distributed through its tissue like a supply depot scattered across a city. But iron has a second nature. When a stray hydrogen peroxide molecule, the kind that superoxide dismutase produces, the kind that catalase is supposed to sweep up before it lingers, meets a loose iron atom, something happens. The iron hands the hydrogen peroxide an extra electron, and the hydrogen peroxide becomes something far more reactive than it was, a molecule hydroxyl radical. No enzyme in the brain is fast enough to catch a hydroxyl radical before it grabs at whatever is nearest. It does not wait. It reacts on contact. Researchers call this the Fenton reaction, after the chemist who first noticed it, though the name matters less than the mechanism. The mechanism is this: hydrogen peroxide, which is dangerous but manageable, becomes hydroxyl radical, which is not manageable at all, and it does so with the brain's own iron as the catalyst. The iron is not consumed. It walks away from the reaction and does it again. Ollie knows this. This is why the upstream steps matter so much. Superoxide dismutase handles the first reactive fragment, superoxide, and converts it to hydrogen peroxide. Catalase then handles the hydrogen peroxide before it can drift toward an iron atom. The chain is not just sequential for tidiness. It is sequential because each step removes the feedstock for the next more damaging reaction. Miss a step, and the iron waiting in the tissue can take over. The Fenton reaction is not a failure of the antioxidant system. It is what the antioxidant system is specifically designed to prevent. And the brain, of all organs, has the most reason to worry about this. Not because the brain is fragile, it is not, but because it holds more iron than almost any other tissue, and because its membranes are lined with exactly the kind of fatty molecules that a hydroxyl radical finds easiest to grab. Lipid peroxidation, the chain reaction through fatty membranes that an earlier part of this night described, is far faster and far harder to interrupt when a hydroxyl radical starts it than when a less reactive fragment does. The Fenton reaction is, in a quiet way, a multiplier, so sleep matters here in a very specific fashion. Not just because the antioxidant enzymes can run at fuller tempo when they face less competition, but because catalase, the enzyme that converts hydrogen peroxide to water, is one of the first to slow down when the cell's shared resources are stretched thin. The waking brain, burning fuel at its full daytime rate, stretches those resources. Hydrogen peroxide does not accumulate to dangerous levels under ordinary circumstances, but it lingers a little longer. The gap between production and clearance widens just slightly, and each molecule that lingers is a molecule that might find an iron atom. As sleep deepens, that gap closes, the fuel demand falls. The shared cellular resources that hydrogen peroxide clearance competes for, the same carriers that power the glutathione recycling loop, the same ones that NAD keeps replenishing, are no longer pulled in quite so many directions. Catalase runs at its natural pace. The hydrogen peroxide is met promptly. The iron in the tissue stays quiet, because the molecule that would wake it up is removed before it arrives. This is not a dramatic rescue. Nothing in Ollie's work is dramatic. It is a narrowing of opportunity, a reduction in the margin where the Fenton reaction might otherwise find its opening. The brain does not become invulnerable. It simply becomes a little less permissive of the conditions that let hydrogen peroxide linger near iron. Ollie moves through the tissue with the patience of someone who has done this many times. The myelin corridors, the gray matter, the deep nuclei where iron concentrations run highest. Each pass removes a little more of the hydrogen peroxide that the upstream enzymes have produced. Each pass narrows the window a little further. The brain's iron stays in its depot. It does the work it is supposed to do, building, transporting, signaling, without being recruited into something it was never meant for. Ollie knows this dark. The iron, the hydrogen peroxide, the narrow window between one and the other, the whole architecture of the Fenton reaction, and the even quieter architecture of the system that keeps it from running. It did not make the night simpler. It made it necessary. You are further from waking now than you were a few minutes ago. That is the whole direction of travel, just down and quieter. Here is something worth sitting with for a moment. The brain does not just burn fuel, it thinks. And thinking, the actual electrochemical business of forming a memory, linking an idea, quieting a worry, is itself a source of reactive fragments. Not a dramatic source, not a flood, but a steady, insistent one, layered on top of everything the mitochondria already leave behind. Ollie knows this. Every synapse, the tiny gap where one nerve cell passes its signal to the next, is a place of high activity. Neurotransmitters cross the gap. Ion pumps push charged particles back into place. Receptors reset. All of it costs energy, and wherever energy is spent at speed, the mitochondria nearby run hot. And some fraction of that burning leaves a stray fragment, drifting in the local space. Through the waking hours, the synapses fire in their thousands, in their millions. The fragments accumulate at precisely the spots where the brain's most delicate machinery lives. The receptor proteins that receive signals, the membranes thin enough to change shape in response to a passing electrical wave. These are not places you want reactive debris lingering. So the antioxidant crew has learned, over a very long time, to concentrate there. Glutathione, the brain's primary cleanup molecule, assembled from three simple building blocks the cell keeps on hand, is present in higher concentrations near active synaptic zones than almost anywhere else in the brain. It is not distributed evenly, like paint on a wall. It is positioned, leaning toward the places that need it most. That positioning takes resources. The enzymes that regenerate spent glutathione back into its working form need the shared cellular currency, that cycling carrier that threads through hundreds of reactions at once to do their work. During the waking hours, that currency is being claimed from many directions at once. The synapses are firing. The ion pumps are running. The mitochondria are spinning up to meet each fresh demand. The glutathione recycling loop gets its share, but the share is uneven. Sleep changes the arithmetic. When the firing slows, when the long chains of waking thought finally go quiet, and the brain settles into its nighttime rhythms, the demand on the shared cellular currency eases. Not everywhere at once, and not all the way down. The brain remains active during sleep in ways that matter enormously. But the particular kind of activity that burns fuel at synaptic speed, moment to moment, in pursuit of the next thought. And in that easing, the glutathione recycling loop finds room to run. Ollie works the synaptic zones carefully. The membranes here are not like the long white matter corridors he covered earlier. Those are highways, long stretches of fatty insulation wrapping the brain's communication cables. The synaptic zones are more like junction boxes, compact, crowded, chemically busy, even in sleep. And the reactive debris they collect through the day tends to settle in close proximity to the proteins that matter most. The receptor proteins at a synapse are, in a sense, the brain's listening apparatus. They receive the signal. They change shape briefly, a precise, controlled change. And that shape change is how information moves. A receptor that has been touched by reactive debris in the wrong place may still respond, but it may respond a little differently, a little less precisely. The shape change over time becomes less reliable. This is not a sudden event. It does not happen in a night or a week. It is the slow accumulation of small imprecisions, the kind researchers describe when they talk about the ordinary, gradual change that comes with age. Not a collapse, a drift. The antioxidant system at the synapse is, among other things, a defense against that drift. Glutathione, positioned near the receptor proteins, intercepts the fragments before they reach the machinery. The spent glutathione is returned to working order. The receptor stays precise. The signal crosses the gap cleanly. And this is the part that takes a moment to absorb. The same synaptic zones where all of this debris management happens are also the zones that consolidate memory during sleep. The brain, while the body is still, quietly strengthens the connections that the day made provisional. It replays, it reinforces, it prunes what was not useful. The cleanup and the consolidation share the same geography. They happen in the same quiet hours, in the same cramped junctions, drawing on the same reserves that the waking day had stretched thin. Ollie does not find this surprising. He has worked these corridors long enough to know that the brain rarely wastes a process. If the night is already the time when the antioxidant crew has room to run. Then it makes sense, a deep structural kind of sense, that the brain uses the same window to do its other careful work. The two processes do not compete. They coincide. Lars, moving his fluid currents through the broader corridors nearby, manages the larger debris, the misfolded proteins and metabolic byproducts too big for Glutathione to handle. Ollie handles the molecular level. Between them, the synaptic zones get what the day could not fully provide. Neither of them would call it elegant. That is not the vocabulary of maintenance work. But it is, in its quiet way, extraordinarily well arranged. Ollie knows this hour. The brain did not put its cleanup crew next to its memory machinery by accident. It made them the same crew. The night is deep now. Deep and still and very comfortable. There is nothing to do here. Nothing to solve. You just need to be present, in this quiet, in this dark. The brain did not put its cleanup crew next to its memory machinery by accident. It made them the same crew. And here is something that follows naturally from that. Something easy to miss if you think of the antioxidant network as a simple mop. A mop moves in one direction. It removes what it finds. It does not adjust. The brain's antioxidant system is something considerably more interesting than that. It reads the room. It adjusts. It scales its own response to the level of debris it is encountering. And it does this by listening to the very fragments it is meant to clear. That is the part worth sitting with for a moment. Reactive oxygen fragments, the stray exhaust of a cell burning fuel, are not only waste. In very small quantities, in brief and bounded bursts, they carry information. They are a signal, not just a mess. The cell uses their presence the way a goodnight janitor uses the state of a floor, not just as something to clean, but as evidence of how the evening went. When the signal rises, when the level of reactive debris climbs past a certain threshold, a particular protein inside the cell unfolds and moves. It travels into the nucleus, which is the cell's control room, where the instructions for building proteins are stored, and it reads out the instructions for more antioxidant machinery. More of the enzymes that break reactive fragments down. More of the building materials for glutathione. The cell responds to the load by expanding its own capacity. This mechanism, the process by which reactive fragments trigger the production of the very proteins that clear them, carries a formal name, a pathway called NRF2 signaling. The NRF2 protein is the one that moves. It is sometimes described as the master regulator of the antioxidant response, and that is not too dramatic a description. It is the system's volume knob. Ollie knows this. He has watched it operate in every corridor of the brain, and the remarkable thing is what happens to that volume knob while you sleep. Through the waking day, the signal of reactive debris runs high, not dangerously, but steadily. The cell's fuel consumption is constant. The neurons are firing, The demand on every shared resource is continuous. The NRF2 protein moves when it must, but the antioxidant machinery it calls into being takes time to assemble. There is always a slight lag between signal and response. That lag is small enough not to matter most of the time, but it does mean the system is always running just a little behind. Sleep changes the arithmetic. As fuel demand drops and the firing quiets, the steady stream of reactive debris narrows. The signal that drives the NRF2 response does not vanish. A resting cell still burns fuel, still releases stray electrons, but it settles into a register the cell can manage without urgency. The antioxidant machinery that was assembled in response to the day's load keeps running. The enzymes are there. The glutathione recycling loop is turning. And the demand on the system has eased just enough that the capacity and the load are no longer chasing each other. The lag closes. That is the quiet achievement of this particular hour. Not a sudden flood of cleanup, not a dramatic restoration, just a system that had been running fractionally behind all day, finally pulling even with itself. In the brain's gray matter, the dense neuron-rich tissue where the day's thinking happened, the NRF2 pathway is not idle as sleep deepens. It is recalibrating. It is reading the reduced signal and adjusting the antioxidant network set points for what comes next. The capacity that sleep allows to be assembled will still be in place when morning arrives and the fuel burning resumes. This is why the night matters not just as cleanup, but as preparation. The brain does not simply clear what the day left behind. It uses the information carried in the day's debris to decide how much capacity to build for the next day's demand. The reactive fragments are, in that sense, a kind of ledger, a record of what was asked of the system, and the cell reads the ledger carefully, then spends the quiet hours building accordingly. Ollie moves through the gray matter slowly. There is no urgency in the movement. The neurons are still. The synaptic zones are doing their memory work in that other register, the one that doesn't need him to stand aside. He passes through the cortex, along the layered tissue that sits just beneath the skull, where the day's most demanding thinking was done, and where the reactive debris ran thickest through the afternoon. The NRF2 response is already ahead of him in some corridors. The new machinery is assembled. The glutathione loop is turning at a steadier rate than it managed at 2 in the afternoon. The tocopherol relay is restored. The catalase stations are clear. He does not need to hurry. The system is reading itself, adjusting itself, preparing itself, and he is simply the presence that confirms the work is being done. The antioxidant network does not wait to be told the day was hard. It reads the evidence and responds before anyone thought to ask. It did not make the night quieter. It made it instructive. Everything is quieter than it was a moment ago. Even the small sounds have gone soft around the edges. There is something worth pausing on before the night moves any further. All through this quiet hour, the attention has been on what gets cleaned up, the reactive fragments, the spent glutathione, the hydrogen peroxide caught before it finds the iron. The debris side of the balance, but a balance has two sides, and Ollie, moving through the brain's dimmed corridors, has always understood both of them. The other side is where those fragments come from in the first place. Not in a general way, in a very specific structural way. The mitochondria, those elongated amber-colored power stations that Mia manages across the body's 37 trillion cells, do not spend the night simply idling. They reorganize. And in that reorganization, something happens to the rate at which reactive fragments are produced that changes the nature of Ollie's work from the inside out. Here is the thing about mitochondria that almost never gets mentioned. They are not fixed objects. They are dynamic. During the waking hours, the brain's power stations run in a more fragmented state. Smaller, more numerous, spread across the cell, each one burning fuel independently. More surface area, more throughput, more exhaust per unit of time. It is exactly what a brain under load requires. The cost is proportional. But during sleep, as fuel demand eases and the electrical chatter of the neural network settles, something shifts. The mitochondria begin to merge. Small fragments fuse into longer, more interconnected structures. The network pulls together rather than spreading apart. Researchers call this process mitochondrial fusion. And the opposite, when they split apart during high demand, is called fission. Fusion does several things at once. A larger, more connected mitochondrial network is more efficient. It shares resources across its length, passing electrons, distributing membrane potential, evening out the workload. And an even workload means fewer bottlenecks. Fewer bottlenecks means fewer moments when an electron gets stranded at the wrong point in the chain and slips sideways to become a reactive fragment. Ollie knows this. The production of reactive debris does not stop during sleep. And it slows not because the mitochondria are resting in any passive sense, but because they have restructured into a form that runs more cleanly, less fragmented, less leaky. Less likely to hand Ollie a pile of reactive fragments that exceeds what the cleanup crew can handle. Mia would phrase it more plainly if asked. She would say that every station leaves something behind, and that the overnight audit is partly about deciding which stations should run and which should be quietly retired. That second part, the retirement of underperforming power stations, a process called mitophagy, meaning the cell's own system for dismantling worn mitochondria before they become a source of excess debris, is also a feature of the sleeping brain. A worn mitochondrium leaks more. Its inner membrane, where the energy conversion happens across the folded ridges called cristae, loses its tight organization over time. Reactive fragments appear in greater numbers, not because fuel demand is high, but because the machinery is fraying. Mitophagy is the quality check. The brain uses the quieter hours, when ATP demand has eased and the cellular machinery has room to attend to maintenance, to flag the worn stations and begin their orderly dismantling. The result is that the mitochondrial population of the sleeping brain trends, slowly and incrementally, toward better quality, not dramatically, not all at once, but across enough nights, the composition shifts. A higher proportion of well-organized, efficiently running power stations means a lower baseline rate of reactive fragment production. And for Ollie, that changes everything about the morning. Not because the work disappears. The work is always there. Reactive fragments are the ordinary exhaust of a living cell, and a living cell never stops producing them entirely. But there is a meaningful difference between arriving at a corridor where the debris has accumulated just above the crew's working tempo, and arriving at one where it has accumulated far beyond what the tools at hand can reach. The first is maintenance. The second is something else, a slow structural tilt in the balance that does not correct in a single night. The fusion-fission cycle and the quality control pass that runs alongside it are the brain's way of addressing the production side of the ledger, while Ollie addresses the clearance side. They do not coordinate in any conscious sense. There is no signal passed between them, no schedule agreed upon. They simply happen in the same window, during the same easing of demand, using the same freed-up resources. Ollie moves through a corridor near the base of the brain's folded surface, where the myelin-wrapped pathways run deep and the mitochondria are dense. The debris here is lighter than it was an hour ago. Not because anything dramatic has occurred, because the power stations in this corridor have been running in their merged, more efficient configuration for long enough that the output has simply been cleaner. The floor is easier to sweep when less has been spilled. That is not a reduction in the importance of the work. It is the point of the work that enough consecutive nights of proper rest allow the brain to arrive at morning not merely cleaned, but slightly better organized than it was the night before. It did not make the night simpler. It made it cumulative. Your body has done this every single night of your life. It knows the way without being told. Let it lead. The brain is quiet now. Not silent. It is never truly silent, but quieter than it has been all day. The signals that crossed and recrossed through those synaptic junctions have slowed. The fatty corridors of white matter lie still, and Ollie moves through them the way a careful worker moves at the end of a long shift. Not hurrying, not stopping, just continuing. This is what the deep hours feel like from the inside. Not dramatic, not sudden, just a slow settling, like dust coming to rest on a still floor. The reactive fragments are fewer now, not gone. They are never entirely gone, but fewer. The busy firing of the waking brain slowed hours ago. The fuel burning eased, and with it, the steady exhaust of that burning eased too. The debris load drifted down, and the cleanup crew found itself, for the first time all day, working with enough room to breathe. Ollie knows this. The antioxidant machinery, that layered, quiet relay of tools that the brain built for itself, has been running at something close to its full tempo for a while now. The recycling loops are cycling. The two-step sequence up front is converting the most reactive fragments into something simpler, something harmless. The membrane defenses are holding. It is not a victory, it is a balance, and balance is enough. Think of it this way. Through the waking hours, the cleanup and the debris were always close to even, sometimes tipping one way, sometimes the other. The brain always manages during the day because it has to, but managing is different from restoring, and the deep hours of sleep are when restoring happens. Slowly, quietly, one membrane at a time. The shared resources that the antioxidant loops depend on, the cellular currency that powers the recycling, the repair, are no longer being pulled in a dozen directions at once. The day's competing demands have stepped back. What remains is the work itself, running at its own pace, without interruption. And somewhere in those fatty, lipid-rich corridors, the myelin that sheathes the brain's long signal pathways is a little steadier than it was at dusk. Not remade, just maintained. Just held at the level it needs to be held. That is the quiet promise of this hour. Not transformation, maintenance, the slow, faithful return to a balance that the day's work spent down. Ollie has always understood this. The brain does not ask for more than it needs from the night. It asks for enough. Enough clearance, enough recycling, enough repair, enough to begin again. The synaptic zones, those small specialized junctions where the day's signals gathered and memory began to settle, are holding steady now. The glutathione concentrated there through these quiet hours has done its patient work. The reactive exhaust of all that daytime firing has been met and quieted. The junctions are calm. Calm is not nothing. Calm is what the brain was asking for. And the mitochondria, those small, warm power stations scattered through every neural corridor, are continuing their slow nighttime reorganization, merging where they had fragmented, producing a little less reactive exhaust with every passing hour. Ollie and the power stations do not coordinate in any way that could be called a conversation. But they are working in the same direction, in the same hours, without needing to discuss it. This is how the body does most of its best work, quietly, without announcement, in the dark. Let your breath settle. Let the weight of your arms rest where they have fallen. The pillow is cool at the edges. The room is steady. There is nothing that needs your attention right now. Not one thing. The brain is being looked after. That is not a figure of speech. It is biology. The same biology that has been running quietly and reliably every night for as long as you have been alive. It does not need your help to do this. It only needs the dark and the stillness and a little time, all of which are already here. Ollie moves through the last of the corridors. There is no finish line, no final task that marks the shift's end. The work tapers rather than stops. The balance holds rather than arrives. And that, in its own way, is exactly right. Ollie knows this hour. The deep hours are not the end of the night's work. They are the proof that the work has been going well. The brain, quieter now than it has been since morning, is doing what it has always known how to do. Restoring. One quiet corridor at a time. Notice how easy the breath has become. Coming and going, coming and going. You are not managing it. It knows the way on its own. Restoring, one quiet corridor at a time. The brain is somewhere far beneath the noise of the day now. The membranes are still. The fatty corridors lie easy in the dark. And Ollie moves through them the way he always does. Unhurried, steady, with no sense that the work could ever be anything other than this. Not fast. Not slow exactly, just the right pace for a night that has nowhere to be. The reactive fragments are fewer now. They have been fewer for some time. The loops have been running. The two enzyme sequence breaking the most reactive debris down, step by careful step, into something harmless. Superoxide becoming hydrogen peroxide becoming water, simple, orderly, as reliable as the turning of a wheel that has been turning a very long time. And the glutathione keeps cycling, spent and then restored and then spent again. The shared cellular currency flows quietly through the whole network, powering the recycling loop without friction, without interruption. Because there is nothing else competing for it now. The day asked for so much. The night asks for very little. Ollie knows this. The white matter corridors, those long, lipid-rich paths wrapped in their layered sheaths, have been gradually quieting through the deep hours. The chain reactions that might have started earlier have been interrupted. The relay held. Tocopherol, ascorbate, glutathione, lending and returning, in the slow rhythm of a system that has found its pace. And in the synaptic zones where the day's signals once moved so fast and so often, the glutathione sits at its highest concentration, ready, still, barely needed now, because the debris has thinned to almost nothing. This is what the night is for. Not drama. Not effort, just the patient accumulation of small restorations. Each membrane a little more intact than it was an hour ago. Each recycling loop a little more settled. Each corridor a little quieter. The brain does not announce this work. It simply does it, the same way it does everything it does best, without asking for recognition, without waiting for applause. Somewhere in the same quiet, the mitochondria have been reshaping themselves, merging into longer, more efficient networks, leaking fewer stray electrons into the corridors Ollie tends. The worn ones have been retired, gently, without ceremony. The ones that remain burn their fuel a little more cleanly than before, which means the debris load tomorrow starts from a cleaner place than today. Ollie doesn't think about tomorrow. That's not how this works. There is only the corridor he is moving through now. Only the fragment he is quieting now. Only the membrane that sits a little more easily because of what has happened in this hour. The NRF2 signal has settled. Earlier, it was reading the debris and adjusting, calibrating the antioxidant machinery for the day ahead. Now it is simply quiet. The calibration is done. The cell has made its small preparations and returned to stillness. This is what balance feels like from the inside. Not triumph, just evenness. Just the hum of things working the way things work. Ollie moves through a stretch of membrane near the long relay corridors. The white matter, always the most vulnerable, always the most lipid-rich. He has been through here before. He will come through again before morning. That is fine. Repetition is not failure. Repetition is the work. The brain is a large place, and the corridors are many, and one pass is never quite enough. But in these deep hours, and this is one of the few times the distinction earns its place, the passages are cleaner than they were when the work began. That much is clear. Ollie knows this dark. The breath in the room is long and easy. The body has stopped asking questions. The muscles have let go of the small tensions they carry through the day without anyone noticing. The brain, wrapped in its membranes, surrounded by its fluid channels, tended by its invisible crew, is resting in the way it rarely gets to rest. Fully, quietly, without interruption. And Ollie keeps moving, not because there is urgency, not because the work is almost done, but because this is what he does in these hours, in this stillness, in this brain that burns so much and asks the night to restore what the day takes. One corridor at a time. One membrane at a time. Slowly, steadily, as the deep hours hold. Notice the weight of your head on the pillow. Heavier than you thought. Let it be that heavy. And here, near the edge of the night, the work is nearly done. Not finished in the way a task is checked off a list, done in the way a tide comes in and goes out, fully, faithfully, without announcement. The brain rests in its own quiet hum. The fatty corridors are tended. The synaptic zones, those small crossings where signals leapt all day, are settled now. The glutathione recycling loop turns at its easy tempo. The 2-enzyme sequence, the one that breaks the most reactive fragments into hydrogen peroxide, and the one that breaks hydrogen peroxide into water, has been running through the small hours without interruption, without competition, without rush. Ollie moves through the last corridors the way he always moves. Unhurried, attentive to nothing dramatic, only to the ordinary accumulation of a day's burning. He passes the white matter's long myelin sheaths, those fat-wrapped cables that needed tending most. He passes the mitochondria, now reshaped into their leaner, more efficient networks. Less exhaust left behind than at the evening start. He passes the places where NRF2 quietly calibrated the next day's defenses, writing the night's chemical experience into tomorrow's readiness. He does not announce any of this. Ollie knows this. Lars, the manager of the brain's fluid drainage channels, those slow cerebrospinal rivers that carry the broader molecular debris toward the body's waistlines, has made his own passage through these same corridors. Their work does not overlap. It does not compete. Two careful systems sharing one quiet geography, doing exactly what they came to do. The balance holds. Not perfectly, because nothing biological holds perfectly. But well enough. Better than this morning, better than mid-afternoon. The margin between the debris load and the antioxidant crew has widened again, gently in a way sleep is designed to widen it. One cell at a time, one corridor at a time, one quiet hour at a time. The brain is not idle when you sleep. It never was. It is simply doing a different kind of work, the kind that cannot happen any other way, in any other window, at any other hour. And Ollie will be here when morning comes, as he always is, as he always has been. While you sleep, Oxidative Ollie is already at work. He moves through the brain's fatty corridors, those long, lipid-rich stretches wrapped around every signal, every memory, every quiet resting thought, sweeping the reactive oxygen fragments that the day's fuel burning left behind. The glutathione recycling loop turns without interruption. The 2 enzymes upstream convert the most reactive debris into plain water, step by careful step. The antioxidant and the repair run side by side through the same dark geography, sharing the same window, restoring the same balance. You don't have to do anything. Your body knows exactly what to do. It's been doing this work for your entire life, every single night. So let it, trust it, and as you drift deeper now, Oxidative Ollie will be here when you wake up. Quieter, calmer, better. Sleep well.